2.6, we got through most of it, but there are a couple of examples that I would like to finish, particularly an inequality example at the end. If you guys did work through your homework yesterday, one of your last problems was an inequality problem, and if you guys weren't sure how to do it, I figured, well, let's just go back and finish these examples first, and then that'll probably clear up most of their questions. Okay, all right, real quick recap as to what we're doing. Again, working with laws of logarithms. One of our objectives yesterday was to expand and condense logarithms. We got to that part of it, right? We spent some time doing expansions and condensations. No, that's not right. Condensings, right? Of some of our different logarithms, okay? And then we started working with solving equations of our logarithms as well too. But there were a couple more that I wanted to finish, okay? So big things, I mean, we talked about some of these simple values as well too. But then when it came to expanding and condensing, we did our product, our quotient, and our power property. And that kind of ruled a lot of what we did yesterday, okay? So we looked at how to expand and condense in some very simple formats. So we did some of these as well too. And then we got to the intense stuff. So we looked at much more intense logarithm. We condensed it down into one nice, neat, single package. Usually when we are condensing logarithms, we end up with a log of just one expression, whether it's a fraction or not. And a big thing that I talked about, and I think I did it on this slide, is when you have two logs that are subtracted from each other, you need to make sure you condense it as log of a fraction instead of one log divided by another log. So that was a big thing that I talked about yesterday that I wanted to make sure that you guys remembered going into what we're going to do today as well too. Okay? All right. So we went through these, and then you guys had a couple of problems in your homework where you had to solve equations that were just like this. So we talked about using product property to condense things back together, so that way we could solve both sides of our equation. Now, honestly, the only thing that I care about you remembering from yesterday is my favorite word. What is my favorite word in all of math? Yes, exactly. So we did that yesterday, right? We had the opportunity to exponentiate in order to solve some of our equations, right? So like, for example, this middle equation, once we condensed it into log of a single expression, we exponentiated both sides of the equation, meaning make both sides an exponent with the same base in order to cancel out the log, and then we solve from there. We'll have the opportunity to do that here again in a minute. Okay, so let's do this. We want to express y as a function of x, meaning we want to explicitly express y, okay? And then it says the constant c is a positive number as well too, okay? All right, so I want to condense and I want to solve for y. What properties would you expect we use in this problem? What do you think? What property would you foresee us using? Product, right? Because why? It's addition. We've got logs of the same base that are added to each other, right? Okay, nothing much I can do on the left side. So natural log of y equals. So what would my left side look like? We can do it all in one fell swoop if we want, right? Because we have log of three different logs that are added together. But we could also step it out into parts. What would our right side look like? What do you think? Ethan?
You could do like ln c plus ln in parentheses x squared plus x.
It's natural log of c plus natural log of, you said x squared plus x?
Yeah.
Okay. What did you do to get from step 1 to step 2?
Well, I don't want to put ln c at the end, so put it at the front.
Okay. Because usually constants go in the beginning. Okay, I like it.
And x times x plus 1, because those are added.
Good. So you started by combining these two log expressions together to get this expression right over a chair. And then you distributed the x to both of those terms to get x squared plus x. Okay, I like that. So then what's my next move? Can I do it again? Yeah, because I'm still adding a log, right? So now we just make it natural log of, do some brackets if we want, c times x squared plus x inside of my brackets, right? Okay. Now I want to write it as y as a function of x. So what should I do for my next step?
Well, you could take everything to the long to everything, right?
There's a word for that.
Exponentially.
There it is. What base are we going to use?
Oh,
E, right?
Yeah.
So we should exponentiate both sides of our equation. That way we cancel out our natural logs, okay? And we end up with y equals, exponentiate the right side as well too, c times quantity, x squared plus x. If I want to distribute the c, I can. I wouldn't necessarily say that it's important that I do. I feel like that is a sufficient expression. Okay? All right, we good there? Using more properties of logs. Okay, all right. Okay, let's deal with just some individual expressions instead of an equation for a change. Okay, so no equal sign, so we're dealing with an expression here. So I got 4 to the third power plus log base 4 of 5. This will actually require us to think back to our properties of exponents from a couple of sections ago in order to figure these out. So 4 to the third plus 4 to the log base 4 of 5. It's a little strange. Well, I'd rather you guys tell me. What's a little different about this problem that we don't usually see? There's addition in the exponent. We've done a lot of stuff like that. But we've added exponents before, right? What do we do, or what are we given that usually results in us adding exponents together? Multiplication. So like multiplication of what, Andy? 2 exponents, right? With the same base you said. So for example, if I had like 4 to the a power times 4 to the b power, that equals 4 to the a plus b. So then, are you guys thinking what I'm thinking? Kind of like deconstruct that property and work in the opposite direction, right? So how could I rewrite this expression such that it uses that property that we learned before? Ooh, I like it. 4 to the third times what?
5.
Well, so you're thinking like 4 steps ahead, as a mode typically is. But what would I write if I didn't simplify it already?
4 log 4 of 5.
Yeah, 4 to the log base 4 of 5. Okay, so I can split that up using multiplication. But then Amog, what did you do?
I remember like the thing from the last chapter. Since like 4 are the same, then it's just 5.
Right. So when I have 4 raised to the power of log of that same base of some sort of argument, I can cancel out those terms, and I do end up with 4 cubed times 5. So that's where that 5 came from. Okay? All right. What's 4 cubed? You guys are smarter than I am. You know these values better than I. 64. All right. What's 64 times 5?
320.
320. All right. So my answer is 320. You okay with that? Yay. Let's do the next one. This next one's pretty similar, but what am I going to do this time around? We're going to divide, right? So what goes in my numerator? The non-Amog version, the slow stepped out version. What goes in my numerator? Got to divide 2 things. What do you think? Lulu, unfortunately for you, I'm sitting behind you. So what do you have on your screen? What goes in my numerator?
E to the exponent of natural log 2.
Good. So e to the natural log of 2. You guys like that? Okay, then what goes in the denominator? Oh, very good. E to the 4th power, right? Okay, cool. All right, what happens up top? Cancels out into a 2, right? I like it. Okay, so 2 over e to the 4th. Is there anything I can do with that bottom? Now, we don't want to make it a negative exponent, right? So I think we leave it like that. Sound good? Okay, cool. Yay. All right, uno más. Okay. You do have a problem in that assignment that I gave you yesterday that has you solve using an inequality. So I want to do a problem like this. We have log of 5 minus x minus log of 7 is less than 0. Okay. I mean, we're going to treat this nearly the same way that we would treat an equation that has equality. So nearly the same way as if it was equal to 0, okay? And we'll proceed pretty much in the same manner. What do you think our first step looks like? Especially based on the type of stuff that we just did. What do you think? What are we going to start by doing first? Michael? Quotient property. So you want to combine both those logs together and make it a fraction inside the log?
Yeah.
Okay. So what's that look like?
You have 5 minus x over 7.
Cool. Less than 0?
Yes.
Okay. I like it. Now, if it was equal 0, what would you guys do next? You said what? Amog, there's a better word for that.
1.
Huh?
1.
Nope. Oh, yeah, you're right. 10 to the 0th power is 1. But what's the word I'm thinking of?
Exponentiate.
There it is. Say it again for the people in the front.
Exponentiate.
Exponentiate. So we're going to exponentiate both sides with a base of what? What's the base of my log? 10. It's not listed there, so what's the name of that log if there's no base there? Common log. So we do base of 10, exponentiate both sides. Okay, cool. So then on the left side, we cancel out the 10 and the log, and we're left with 5 minus x over 7 is less than 10 to the 0th power is going to be what? 1. So that's that value that Amog was talking about. Okay, cool. What do I do next?
Doesn't this have 2 cases?
It will have 2 cases. Yep, we're going to get to that in just a second. Actually, we'll get to it now. Ethan, let's talk about it. What's our other case?
X is less than 0.
Close. What do we need to make sure with the input of our logarithms?
It's positive.
It's got to be positive.
5 minus x
5 minus x
is greater than
has to be greater than 0. Now, what type of inequality would we consider this? You think it's an and or an or? And. Both have to be true, right? Like, we have to have 5 minus x being greater than 0. So we'll solve both these inequalities in tandem, all right? So getting back to the left side there, 5 minus x less than 1, what should we do to get to x?
7.
Okay, so 5 minus x less than 7. And then what should I do? We'll just focus on this one for now. We'll solve the other one in a minute. Subtract 5, right? And then negative x less than 2. And then divide by negative 1. What do I need to remember to do? Flip the sign. So I need x to be greater than negative 2. Okay? All right, back up to the top, though. Ethan is right. He pointed out that this is going to be an inequality where we have to solve 2 different cases. We have to be careful about our domain restriction. Our inputs have to be greater than 0. Okay, so add x to both sides. I get 5 is greater than x. But I'm going to be honest with you guys. I don't like writing it like that. I like my variable on the left side. Is that our u r? It just makes more sense to me that way. Okay, so how would I write that? X is what?
Less than
Okay. So I need x to be greater than negative 2, but less than 5. So let's toss that on a number line, write it as an inequality, and then we should be good. Okay? So I need the overlap of x being greater than negative 2, and then x being less than negative 5. So I want all the values between what?
-2 and 5.
Very good. We're talking open circles throughout. Negative 2 and 5. So negative 2 is less than x, which is less than 5. How do we feel? We good? Okay, super. Any of the problems that you guys want to see from yesterday's homework?
We have to like simplify the e.
2 over e to the 4th?
Yeah.
No, I'm fine with that. That'd be good. I mean, we could get a number out of our calculator, right? but we could have done that in the first place. So 2 over e to the 4th is good. Any of the problems you guys want to see from yesterday's homework? And we didn't fully finish that section, but okay. What about anything for the quiz? I mean, we talked yesterday about like prepping for the quiz and, did a little bit of a review there. Do we need to remind ourselves of the compound interest formula? Would that be a good idea? Do you guys have that memorized yet? Hopefully you do. Okay. Compound interest. Let's say we're compounding n number of times. What is our formula for compounding n number of times? Michael?
A equals P times the quantity 1 plus R over n raised to the n.
Very good. So n is the number of times it compounds in a year. T is our time step. Usually we're talking about a year in this case. And then R is our interest. Now, it is written as a decimal, right? So if I tell you our interest is 4%, what are we plugging in for R? Okay, cool. What about if we're compounding? So compound interest when we're compounding continuously. PERT. A equals PE to the RT, right? The variables mean the same thing. The P is our starting amount. The A is the amount that we end up with. R is our interest rate written as a decimal. T is our time step, number of years. And then E, not a variable. It's a number, right? Okay, cool. Anything else that we need reminded of before the quiz? I think that's the major things. Are you guys okay with writing something as a logarithm and then rewriting it as an exponential? I remember when I went over yesterday, we were like doing this when we were doing some of the problems, right? And that kind of reminded us how to draw the arrows, okay? All right?
Would you go over just like a natural law problem?
Sure. What do you mean by like a natural log problem? Like if I have like natural log of e to the 2x and I wanted you to simplify that?
Yeah, sure.
What could we simplify that to? What is natural log of e to the 2x? 2x, right? Because we could use the inverse properties from before to cancel those things out, and we just end up with 2x. Or if I just have like e to the natural log of 5x minus 4, what could I do there? Cancel them out like before, right? And I cancel those out, and I would have 5x minus 4. Trying to think of like what other type of natural log things we would need to be reminded of. I think that's mostly it. Is that okay? Okay. What about if I had like, I don't know, log base 4 of, I don't know, 16 is equal to x. We know that a logarithm is equal to what? An exponent, right? I know you're giving me the answer of 2, which, Colin, you're right. My answer is 2. But in general, a logarithm is equal to an exponent, right? So what we're hunting for when we're solving for a log is whatever exponent that is going to be equal to, right? So if I rewrite it using the arrows, I always start with what value? The base, right? What does Meghan Trainor say? It's all about that base. I don't like that song. 4 to the x equals, and then we draw an arrow to the inside of that log, right? So 16. So the next is going to be what? Colin already told us, but it's going to be 2, right? Okay. And then we also played the game where, like, I don't know, you raise something to a power and it ends up as a fraction. What type of power would it have to be? What type of exponent would I have to end up with a fraction?
Negative.
Yeah. And then you guys have studied up on your powers, so hopefully we remember some of those. I really can't think of anything else. The only other thing would be like square root is the same as what power? A half. Cube root is a third, so on and so forth. Okay? We ready?
Yeah.
Let's do this. I think we're ready.